All right. This is part 5 of the answers video for the Christmas winter assignment, and we are now on page 13, heading towards page 18. So let's get started on this. So the first question, number 44, is write the formation equation for each of the following. Remember, a formation equation is for 1 mole of a product, so coefficients might be fractions. Over here, I give you what are called the enthalpy of formation. It's how much energy is taken or released in the formation of 1 mole of particular compounds listed over here. There was one typo, so please correct that, and that is for propane. The enthalpy of formation is negative 103.85, so you can go ahead and make that change. Let's go ahead and write these. So the definition of enthalpy of formation is it's the enthalpy, it's the change in enthalpy conditions. Which is 25 degrees centigrade and 1 atmosphere. Okay, so let's read that. So delta H is a change in enthalpy required to create 1 mole of a compound from its most stable elements, or elements in their most stable forms, at standard conditions, which is 25 degrees centigrade and 1 atmosphere. All right, so let's go ahead and fill these in. So for water, so water is made from hydrogen and oxygen. Hydrogen in its most stable form is a gas. It's H2 gas plus oxygen gas is going to give you H2O. Okay, and it can either be gas or liquid. In this case, it's liquid. So we use a scripted L for liquid. This is gas. Okay, and now if we balance this equation, we get 2H2 plus O2 gives us 2H2O. However, the definition states it has to be for 1 mole. So what we're going to do is erase this and turn it into 1 mole. In order to do that, we have to divide everything by 2. And that leads us to a little bit unusual coefficient here of 1/2 for the O2, but that's what's required in order to make that a 1. And then we divide this 2 over here by 2 as well. Again, writing the 1s as coefficients is recommended but not required. And so that's what this equation would look like. All right, same thing for gas. And I'm going to make my 1s in a simpler form. So it's still H2 gas plus 1/2 O2 gas, because those are the most stable forms of those elemental molecules. And the difference is it has a different enthalpy of formation. The reason the enthalpy of formation is a more negative number for liquid water than for gaseous water, which would be steam, is that if you want water to go to a liquid state, you have to take more energy out of it. You have to pull more energy out of it to bring it down from steam, which is this amount of energy, down to liquid water. So therefore, it's a more negative number. More heat has come out of the compound, of the water compound. Okay, CO2 is carbon in solid form, and it's a specific type of carbon. It's graphite. We've learned about that. It's a network solid, a layered solid. That's actually more stable for carbon to be in that form than as a diamond, even though diamonds are the hardest substance on Earth. And so it's carbon as a solid plus O2 as a gas. And that gives you carbon dioxide, 1 mole, which is also gas. Okay, C2H6, also a gas, so it's 2 carbons. And carbon in its most stable form is just a single atom of carbon. Same thing, solid form, graphite. plus hydrogen's most stable form is H2. And to get 6 hydrogens, you're going to need 3 moles or 3 molecules, either way, of H2. That's as a gas. And that's going to give you ethane, 1 mole, which is a gas. Okay, and finally for propane, same thing. Okay, so the formula for the enthalpy of formation method to determine the enthalpy of reaction, delta H of reaction, is all right, so when we write the equation, we're going to start over on the right side here. So what that is simply saying is that it equals three times, and we need the delta H of formation of CO2. We come up here and it's negative 393.5 plus for 4H2O in liquid form, so that's going to be negative 285.8, and it's 4 times that because there are 4 moles. And we're going to put all of that for the product side into some big square brackets. And now we're going to subtract, and we're going to do the same thing on the reactant side. So for C3H8, and it is 1 mole, you want to be, let's see, that is 1 mole right there of this reaction. Actually, it's whatever the reaction is. In this case, it is 1 mole. So C3H8 right here is negative 103, and there's 1 mole of it. So I'll just go ahead and write that. Plus, and oxygen, O2 is 5 moles. But a rule to remember is that the delta H of formation of pure elements, such as O2, H2, anything like that, is 0. It's by definition 0. So it's 5 times 0. We're going to close that in square brackets. Okay, now you have to go through and be careful with the negative signs. Plus, and this one is simply going to be, let me take that back, that's a minus. And it's going to be negative 103. So the negative is going to turn into a plus. And that gives us negative 2, 2, and we're going to just round it to 20 as the final answer. So, we should put units, of course, and that's kilojoules. And since we did it for exactly 1 mole over here, we can put per mole. Okay, not all reactions are done with exactly 1 mole, but the way this one happens to balance out, it is. So it's negative 2,220 joules. Okay, let me check myself. So that is kilojoules per mole. And that is the final answer. That's how much heat will be released per mole of propane that is combusted. Okay, now we're going to move on to a Hess's law problem here. And it says calculate the enthalpy change for the reaction using Hess's law. So Hess's law is like a puzzle. you're going to try to recreate this reaction for which you do not know the enthalpy of reaction from 3 other reactions for which you do know the enthalpy of reaction. So there's 3 things you can do. Let's just review this. One thing you can do is you can reverse a reaction. You can change the reactants over to products and products over to reactants. And what that's going to do is change the sign on the enthalpy. So if you do that, that negative sign, for example, would become a positive sign. The other thing you can do is you can multiply through by a number, by a factor, just like an algebra equation. So you could multiply this by 2, this by 2, this by 2. If you do that, then you've got to multiply this number by 2. And then the third thing you can do, and you do this at the very end, is you add, subtract. So you can add substances that are on the same side of the arrow together, or subtract 2 of the same substances that are on opposite sides of the arrow. So you get a chance to see all 3 of these in this problem. Okay, so let's go ahead and do this one. So what you do, the strategy for this is you look up here at the target equation. This is what you're trying to create. And you pick one of these and you find one of these, the target, that appears only once down here in these 3 equations. So let's go ahead and take graphite. Graphite appears in our final equation. It only appears in this equation number 1. We don't see it anywhere else. It's just pure carbon. So we're going to start with that one. The first thing we notice, and I always like to circle the arrows because they don't usually line up when you do this, and you want to be sure you don't forget which side is right and which side is left. Okay, so graphite. So here we need 2 carbons. Here we only have 1. So what we're going to do is come down here and rewrite this as equation 1A. And we're not going to switch sides. The carbon does appear on the left side of the arrow, which is what we want, but we need 2 of them. So we're not going to reverse the equation, but we are going to multiply through by 2. So we have 2C. That means everything has to be multiplied by 2. 2O2 and 2CO2. I'm not going to bother writing the states. It's not important right now. Okay, the next thing we have to do then is you have to multiply this also by 2. Everything gets multiplied by 2. And that gives you negative 787. The sign does not change. So I'm going to go ahead and put that over here. Okay, and that takes care of that reaction. I'm lightly going to put a line through it to remember that we've used it, because I don't want to add that number in at the end. That's a mistake that can easily be made. All right, next up, we have hydrogen H2 gas right here. And the only place that we see it is right here. So it's on the left side of the arrow here, and it's on the left side of the arrow here. So we don't want to reverse equation number 2. However, it does have a coefficient of 3 here and a coefficient of only 1 here. So we're going to need to multiply this equation by 3. So this is going to be equation 2A. And we're going to multiply by 3. I'll go ahead and put next to it what we did. We multiplied this one by 2. We're multiplying this one by 3. So it's 3H2. And that's going to be 3 times a half is 3 halves. O2. And then we're going to have 3H2O. And we're also going to multiply the enthalpy of reaction, which in these 2 cases is the enthalpy of formation, but it would be whatever normally the enthalpy of that reaction would be. Okay, and that's going to be 285.8 times 3, and that's going to give us negative 857.4. Okay, finally, the last one. Now what? C2H6. So where do we see it down here? We only see it in one place, and it's in this equation number 3. Now, in the target equation, it's on the right side. In equation number 3, it's on the left side. So we're going to have to reverse equation number 3. All the reactants go over to the product side, all the products come over to the reactant side. In addition, we have to, since it only has a coefficient of 1 here and a coefficient of 2 here, we're going to have to divide through by 2. Okay. So I'm going to go ahead and do that in 2 steps. I'll do it in 1 step. But that's normally why we need letter A, B, A, and B, because sometimes you have to do things in more than 1 step. I'm going to go ahead and do this all in 1 step and assume that that won't confuse anybody. If it does, come talk to me. So this is equation 3A. So all of these have to come over to this side. So I'm going to write the coefficients very lightly. It's 4 CO2 plus 6 H2O. And then the arrow, now the reactants go over to the product side, and that's going to be 2 C2H6 and it's going to be 7 O2. Okay, so we reverse the reaction. That means we're going to change the sign on this. Now the other thing we need to do is we need to get rid of that 2 in front of C2H6 because it does not have that coefficient up here. So I'm going to divide everything by 2. I'm going to divide that by 2. That means everything else gets divided by 2. So that's why I wrote these coefficients lightly. So 4 divided by 2 becomes 2. 6 divided by 2 becomes 3. 2 divided by 2 becomes 1. And 7 divided by 2, we'll just go ahead and write it here, is 7/2. All right, so what that means, what do I have to do to this? I have to change the sign and I have to divide it by 2. So when you do that, it gives you 1560, and it's going to be a positive 1560 because of the sign change. Okay, so those numbers should give us the answer. All right, so what we want to do is go through, before we do anything else, and do all of our cancellations. That's our addition subtraction step. Okay, so again, I circle the arrows because they don't line up. I want to be sure I'm keeping which side is which straight. All right, so first of all, we need 2 carbons up here in the final equation. There's the 2 carbons right there. They don't cancel out anywhere, so that's good. We need 3 H2s up here. And there's 3 H2s right there. They don't cancel out anywhere. And finally, we need 1 C2H6 on the right side. There it is right there. And so those are the 3 substances that are going to go into the final equation. It means everything else should cancel out. So let's see if it does. On the right side of this arrow in equation 2, we have 3H2O. And on the left side of this arrow, equation 3, we have 3H2O. All right, next, CO2. On the left side of equation 3, we have 2 CO2. And on the right side in equation 1, we have 2 CO2, so they cancel out. All right, and finally the O2s are a little bit messy, but it works out. On the right side over here, we have 7/2. On the left side of this arrow, we have 3/2. That means there's going to subtract. So 7 minus 3 equals 4 over 2, which equals 2. So what that means is the bigger of those 2 numbers is the 7/2 on the right. So the bigger number minus the smaller is going to leave whatever the difference is over on the right side. So that's going to be 2O2. It's going to be over on this side because the bigger of the 2 numbers was over on this side. So there's a 2O2 there. And we have a 2O2 on the left side of this arrow. So that's going to cancel with that. Of course, we already took care of those. So everything else is canceled out, has a line through it. And so that means these numbers are correct. So now what we do is simply add them up. of reaction of negative 84.4 right there. And if we look up at the top, we see that for this compound, and it is 1 mole that appears, it is, get back down here, for 1 mole of this compound, ethane, and there is exactly 1 mole in this equation. There isn't always exactly 1 mole in the equation, but it happened to be this one. If we come up here for ethane, we get 84.7, negative 84.7, close enough. It's off by a little bit, some rounding error, but that's close enough. So we get essentially the same thing that we got up in the table. So it's just a way of checking our work for this problem. Okay, we're going to move on. All right, 47, compute the enthalpy of reaction combustion for methane using the bond energy method. So remember, the bond energy method is only an approximation because it deals with average bond energies between a typical, for example, carbon-hydrogen bond. It's an average, but carbon-hydrogen bonds don't all have exactly the same energy. Okay, there we go. So it's only approximation. Okay, so we need to get out your table of bond energies. Okay, so to do a bond energies problem, first of all, you need to balance the equation, and it is in balance. So what you do is, it's a little bit like the box method for balancing an equation. You're just going to identify how many of each type of bond you have. I find the bond energy on the average bond enthalpy sheet, and then simply write it in. So let's just go ahead and do it. So we have 1 CH4. So what that means is we have 4 CH bonds. Let's go ahead and write this here. This. So CH bonds, it doesn't matter whether you write CH or HC, it's the same thing. So you have 4 times, and you come over here to the sheet, and it's CH is 413, and it is a positive number. In order to break these bonds, to get this reaction going, you have to put energy in. That means it's positive energy. When you put them back together again, energy comes out. That means it's going to be negative energy on this side. All right, so we've taken care of that. We only had one of those. Okay, now we come on down here, and we have 2 O2s. So the O2s are double bonds. So for O2, we have 2 times. Remember, you have to multiply by however many bonds you have, and then however many molecules you have. So in this case, we only have 1 O2 double bond. And if we look here, right there, there's O2 double bond is 495. We only have 1 of those, but we have 2 different molecules. So it's 2 times 495. So if we do the math on that, this one is going to give us a positive 1,652. And then we're going to add to that positive 495. So that's going to give us positive 990. And I'm going to say plus positive there. So the positive signs are because it's energy going in, and then what you're supposed to do is add these together. Now we're going to come over to the other side, and we have 1 carbon dioxide, and each carbon dioxide has 2 carbon-oxygen double bonds. So it's going to be 2 times, and if we find carbon-oxygen double bonds, it's right there, it's 799. But since these bonds are being put together, it's a negative 799. Energy comes out. Energy has to go in to break bonds. Energy has to come out to when the bonds are formed. They release energy. Remember, things tend to want to go to a lower energy state Otherwise, they generally won't form chemical bonds. All right, and so that's going to give us down here negative 1,598. And then we're going to add to that over on this side, and I'll put big square brackets around this as well. This over here, we have two H2Os. So what that means is we have two HO single bonds, or OH either way. So OH is 463, and that's coming out. If you want to draw the picture, there's two of these, so you actually have this. And then you have a second water molecule. So rather than writing two twice, I'm just going to count up how many bonds I have. So I have 1, 2, 3, 4 OH single bonds. So that's going to be 4 times, and an OH single bond was 463. It's a negative 463 because energy is coming out. And when you multiply those, you get $1852. Okay, so now you go ahead and you combine all of those numbers. And over here we get positive 2642. And I should have, rather than put an arrow there, should have been a plus sign. We're going to add those two. Remember, these are negative numbers over here. So we're going to add that to this. We're just adding up all of the energies on both sides. So it's not a products minus reactants like it was for enthalpy of formation. And that gives us a negative 3450. So now you add those. And it gives us a negative 808 kilojoules. Okay, since it's 1 mole of CH4, it just happens to be in this equation. It won't always be 1 mole of the hydrocarbon. That could also be kilojoules per mole. But it's just really for this reaction, the entire reaction. So that's the answer right there. Okay, let's keep going. And it's asked us to draw some Lewis dot structures down here. So CS2. So we're going to just assume it's symmetrical unless we know otherwise. So what we want to do is count the number of valence electrons. So carbon has 4. So we come over here to carbon, and it's in the second row. 1, 2, 3, 4. It's the 4th element over. So and there's 1 carbon, so it's 4 of those. So 4 valence electrons there. Sulfur, there's 2 of those. And sulfur is the 6th element over in the 3rd row. So it's 1, 2, 3, 4, 5, 6. So it has 6 valence electrons. So that means there's 16 electrons we have to account for. So we go ahead and first create single bonds between the central atom and the outside atoms. That takes care of 4. Now we create octets. So we do that around the outside first. Okay, and if we count, we now have 8 plus 8 is 16. So that's all good. So we have the correct number of electrons. The problem is carbon doesn't have an octet. So what we have to do is move 2 we can't add any more or take away any electrons, so we have to rearrange these electrons in some way to give carbon an octet. And the way we can do that simply is by taking the outside electrons from sulfur and putting them there as a double bond, and doing the same thing on this side and putting them there as a double bond. Okay, so sulfur has an octet, carbon has an octet, both sulfurs have an octet, and so that takes care of that. Okay, let's go on over to HOBr. Now the question is, what's the central atom here? And is it going to be H and then O and then Br, or is it going to be H and Br and then O? Well, bromine is less electronegative, and that would, if you followed the rule that the least electronegative should be in the middle, it would be bromine. We could determine that. I'm just going to tell you what it is. It's HO. It is O in this case, so it's a bit of a violation of that rule. Oxygen is the central atom here. You could determine that by resonance, by a formal charge, but since we're going to do some formal charge problems down below, I'm not going to have you do it here. I'm just going to tell you that that's the correct answer. So let's go ahead and put that together. So we have H. You have one of those. And you have 14 electrons. So when we draw that, it's going to look like this. H can never be a central atom. We knew that. So we're going to form single bonds. Now we're going to form octets around everything on the outside. You can't do any more to hydrogen. You can't put any more electrons there. So right now we've used 10 of the 14 electrons. So now we're going to finish it up by putting an octet around oxygen. And we have 8 plus 6 more is 14. So that's the Lewis dot structure for this. You see, it's not being asked, but what's the domain geometry? What's the shape, the molecular geometry of this? Can you tell? It has 1 for oxygen. Well, oxygen's the central atom. For geometries, you're really only interested in the central atom. So it's 1, 2, 3, 4 electron domains. So that's going to be tetrahedral. The shape is going to be, well, the Ax notation is AX2E2. And that's just like a water molecule, so that would be bent. So it would be bent just like a water molecule. And since it's tetrahedral domain geometry, it would be, if we were going this far, sp3. 1, 2, 3, 4. sp3 is 1, 2, 3, 4. 1, 2, 3, 4. Okay, just throwing those in for a little bit of extra practice. BH3 is an exception to the octet rule. So we have boron. We have one of those. It has 3 valence electrons, hydrogen, 3 of those, 1 valence electron. That equals 6. So we put a B here, and we just put things symmetrically, although I don't like to put things at angles until I know the actual geometry. So we'll just put them like that. And we have 6 electrons, so you need a pair there to bond, a pair there to bond, a pair there to bond. Well, we've used up all 6. And boron still doesn't have an octet. It's because boron is an exception to the octet rule. So that is your final answer right there. Okay, C2H4. So again, we assume it's symmetrical. So it's C. We have 2 of those. Each one has 4 valence electrons. That's 8. We have H. We have 4 valence electron, 4 hydrogens rather. Each one has 1 valence electron, that's 4. That adds up to 12. So now we just draw it symmetrically, a C and a C. We know those have to be the central atoms. And since we don't know otherwise, we're just going to put an H here and an H here, an H here and an H here. All right, so that's the most symmetrical way we could at least initially draw this. We need 12 electrons, so you put single bonds between everything. Right there. Okay, so we use up 2, 4, 6, 8, 10. We need to use up 12. And hydrogen is fine. It has its octet, 2 electrons. Carbons only have 6. So we can solve that problem by adding 2 more electrons there. It's a double bond for ethylene, and that takes care of that. All right. Okay, NCO3. Now it's asking to draw the resonance structures and identify the formal charges on each of these elements. Okay, so let's go ahead and do that. So first of all, we've got to draw the Lewis structure. Electron for the negative sign there. So we have 5 plus 4 is 9, plus 6 is 15, plus 1 more is 16. So you have 16 valence electrons for that. All right, so let's draw it in 2 different ways. We can draw it in 3 different ways, actually. Let's try it all 3 ways here. So we've got N, C, O. We have C, N, O, and we have C, O, N. So we're using all 3 of the atoms as a central atom. We're going to try that out. Okay, we need 16, so let's just do this quickly. There's 1, 2. Okay, so I have 16, but carbon doesn't have an octet. So the way we're going to do that is take these 2 from the outside of this oxygen and take 2 from the outside of the nitrogen. And now everything has an octet, and we've used all 16. Everything has an octet. Now, just to speed things up, it's going to be the same electron configuration for the other 2, so let's just go ahead and write it here to save some time. Okay, so let's go ahead and compute formal charge. For N on this one, it's going to be 5. Let's write the formula out somewhere. Let's write it down here at the bottom. So it's going to be the number of valence electrons for that specific element minus the number of non-bonding or lone pair electrons, not of lone pairs, but of the total number of electrons. So non-bonding electrons minus 1/2 the number of bonding electrons. Okay, and that will give us the formal charge. All right, so it's going to be 5 minus 1, 2, 3, 4 minus 1/2 of 1, 2, 3, 4. And that's going to give you 1 minus 2 is going to give you -1. For carbon, it's going to be 4 minus, there are no non-bonding there, minus 1/2 of all of them are bonding, so that's 8. So 4 minus 4 equals 0. And finally, I'm just going to have to create a little space down here. And finally, for oxygen, for this first one, it's going to be 6 minus 1, 2, 3, 4 non-bonding minus 1/2 of 1, 2, 3, 4 bonding, and that equals 0. And they need to add up to -1 because you had a -1 charge there, so it has to add up to -1 even if it's not the desired structure. Okay. Let's go ahead and do the same thing here. We're going to start with carbon. That's going to be 4 minus 1, 2, 3, 4 non-bonding minus 1/2 of 4 bonding. It's going to equal -2. Nitrogen is going to be 5 minus 0 non-bonding minus half of 8 bonding. That's going to equal 1. And then oxygen is 6 minus 4 non-bonding minus 1/2 of 4 bonding is going to equal 0. So this also adds up to -1. You can see this is less desirable because the numbers are farther away from 0 than this one. So far this one is the one we're looking at. And let's try the last configuration. So we have C, it's going to be 4 minus 1, 2, 3, 4 non-bonding minus 1/2 of 1, 2, 3, 4 bonding. That's going to equal -2. Oxygen is 6. There's none that are non-bonding. Half of the 8 are bonding, and that's going to equal +2. And then we have nitrogen is 5 minus 4 non-bonding minus half of 4 bonding, and that's going to be -1. So if we add -2 plus 2 minus 1, we get -1. So we get -1 for all of the totals. Clearly this one over here on the left is the best. That's why they write the formula in this order, because that's the order of the electrons, similar to HOBr up above. So that's it. All right, let's do the next one is SeO2. So we're just, again, going to assume it's symmetrical until we know otherwise. And Se is 1 times 6 equals 6. And O is 2 times 6 equals 12. Okay, so we have a total of 18. So we're going to put a couple here, and then we're going to surround everything with an octet. Okay, so we now have 16 and 16. We need 2 more. So and put it right. Okay, and so actually I don't want to take that off of there. I have 16 now. I need 2 more, so I'm just going to go ahead and put those right here. And does everyone have an octet? It looks like it right there. And we've used 16, 8, 8, 16, 18. Okay, so it's got 1 double bond and 1 that is not a double bond. And so let's go ahead and go ahead and figure out the formal charge here. So what about this structure? So for this structure right here, we've got oxygen on the left. This oxygen over here is going to be 6 minus 6 minus 1/2 of 2. That's going to equal -1. The Se is going to be 6 minus 2 minus 1/2 of 6. Let's go over that. It's 6 is the number of valence electrons. You have 2 lone pair electrons here, and then you have 1, 2, 3, 4, 5, 6 bonding. So it's half of that 6. So 6 minus 2 is 4, and half of 6 is 3. So 4 minus 3 is 1, +1. And then we have the O on the right, and that's going to give us 6 minus 1, 2, 3, 4 minus half of 4. And that's going to equal 0. So -1, +1, 0 adds up to 0. There's no charge on this, so that should happen. Let's go on to the next one. Let's try putting one of the oxygens in the middle. So we're going to have Se, O, and O, and it's going to have the same electron configuration. 6 minus 6 of lone pair minus 1/2 of the 2 bonding electrons. And that's going to be -1. And then we're going to do the O in the center. I'll call that O sub C. And that's going to be 6 minus, there's 2 non-bonding, and the half of the 1, 2, 3, 4, 5, 6 bonding. 6 minus 2 is 4, half of 6 is 3, that's going to be +1. And then finally we have the O on the right, O sub R. That's going to be 6 minus 1, 2, 3, 4, minus half of the bonding, which is half of 4. 6 minus 4 is 2, half of 4 is 2, so you subtract, you get 0. So you get exactly the same numbers, -1, 1, and 0, -1, 1, and 0. And the rule, if you remember, is that you want the most negative number on the most electronegative element. So if you look at your periodic table or your periodic table of electronegativities, you'll find that oxygen is more electronegative than selenium. And so since in this one, selenium has the negative number, the most negative number, that's the -1. Over here, oxygen has it. Then oxygen is the more electronegative of the two, so this is the one you would prefer. And you want the most negative number of the formal charges on the most electronegative element. And so this first structure with selenium in the middle would be preferred.